Yeah, okay, thank you. Thanks everyone for joining. You hear me talk about named entity disambiguation for Icelandic. I did some robustness evaluation using data augmentation. So it's part of an R&D project I'm working on for a couple of years, developing NLP solutions for the my low resource mother tongue. Talk about the phenomena I'm focusing on, find the problem, talk a bit about the background, and state-of-the-art approaches in relation to what I actually did, and I describe what I did, and my experiments, results, and conclusions. First with the phenomena. So, a seemingly unimportant perturbation can change an AI model's predictions. And worth noting that all this work was done before GPT-4. So it's kind of outdated, but I'm actually talking about large language models, not gargantuan language models. So large language models can achieve this superhuman performance on benchmarks. But when we change the input in the benchmark, drops significantly. And the other phenomenon is data scarcity. So in order to get the power from the large language models, we need a ton of labeled data. It's scarce and expensive to make. Maybe start with this general question. So we have a large language model, fine-tuned it for some task, and we're interested in whether it has learned to make like solid predictions that can generalize, or if it's just cheating. And test this on out of distribution examples or adversarial examples. It's basically has to do with the model learning shortcuts to solve the task and like kind of learning the data set. And yeah, for example, if you want to answer a question about some event that happened, the model can learn to pick up that the word when in the text and realize that therefore there is a question, but doesn't really understand the high level meaning of the question. So table I gathered, so blue, the general language understanding evaluation benchmark, we're supposed to test these models and get fairly close to the human baseline with using the large language model, 80-something%, 91%. Then blue X is an out of distribution version of this benchmark, which was developed recently. And the models drop more than the humans. And I'd like to have a number here, but this is about adversarial versions of the example. So you change the examples a little bit, and then the models fail drastically. Well, I believe the humans, it wouldn't have that big of an effect on people. Yeah, the examples can be changed to the system. And that's kind of what I worked on. So from the general question to the particular questions, so to test the stability, reliability, and adaptability of the language understanding system, measured how well it performed when subjected to small disturbances, and I tried to mitigate the effect of the disturbances. So in the context of entity typing and entity disambiguation tasks, how much does the performance of trained models drop when evaluated on perturbed but semantically valid examples? And can we adapt the models to the perturbations and mitigate the drop in accuracy using data augmentation? It's synthesized perturbations. All the problems to do with data scarcity. The labeled data is crucial for training models and tasks. The data set size impacts the model complexity and accuracy on benchmarks. Large languages benefit from extensive resources, while smaller languages face challenges. For example, so here we have different systems, different evaluation sets, and the highest number here, 97.7%. This is actually superhuman, like slightly larger, higher accuracy than the humans on this set. And that takes 220 million training data points. So a solution to my problem would be to have maybe each Icelander label 1,000 data points, and then we solve the problem, but that's not possible because I have this constraint that my models need to understand the language only spoken by 300,000 people. And state-of-the-art entity models for English are trained on tens or hundreds of millions of examples. While the Icelandic Wikipedia, it's like a source of data, is 50,000 articles, and a data set that we labeled 21,000. We need alternative approaches to achieve good results for Icelandic entity disambiguation. And to do that, use basically transfer learning, multilingual models, experimented with data augmentation, and developed also like a data efficient filters used in the pipeline I made. The concrete questions that I set out to answer for the thesis were how does accuracy vary by training set size for entity typing and disambiguation? And how does it vary on both original and perturbed data? And can we mitigate it thus by thus incorporating synthetic data generated by data augmentation via paraphrasing improve performance? And how does this improvement vary based on training set size? To explain some background concepts. Basically, three main things. The data needs to be constructed. I'll not go into that much. That's like the biggest part of the problem, kind of. But assume we have that in the thesis. Then there's a model pipeline. And then there's what I call a perturber. So I'll talk a little bit about meaning preserving perturbations, the sensitivity of deep neural network. So there's little epsilons here that we kind of perturb the evaluation data, and I perturb the training data and looked at the impact on the system. So what are the tasks? So it's entity typing and disambiguation. Entity typing is assigning a type to a name in a given context. So Turing was a person. Oxford is a location or an organization. And then we have this ambiguity that needs to be disambiguated. I'll just read this definition here. Given a document with names in it and some knowledge base, which kind of defines what exists, the goal is to map each name in the document to its corresponding entity in the knowledge base. That's about linking names to things, thereby assigning unambiguous meaning, basically mapping a string to an identifier. Well, no, it's Alan Turing for 1912, not some other Turing. Here's an example. The two texts that would be input to the system. The Turing Award is given to individuals who have made significant contributions to the field of computer science. And inspired when resting following a lengthy run, Turing conceived the idea of Turing machine in his office, thereby establishing the groundwork for contemporary computer science. Yeah, a bunch of Turings. It's a Turing Award for the person. I know because I understand language, I understand computer science, but how does the computer know? Then we have to make pipelines and systems. It's something I constructed. And there's an okay example to just explain what it's about. If the scroll here is the input, and output is a ranked list of entities from the input. So on March 28th, MJ scored a career high 69 points versus CLE. And I know what this is because I grew up in the 1990s and I've played basketball. But the computer doesn't really know. So we have a pipeline mapping the input to Michael Jordan. Well, it could also be MJ Delaney or Michael Jackson or Mega Shul and a bunch of other things. The entity typing for assigning it a person. In this context, MJ is a person. And then the disambiguation has to do with ranking the different candidates. And the method I used filters based on the person. So manufacturers, junction, railway is not an option. Large language models, when we fine tune them for a task, they learn the necessary features without any feature engineering needed. But it learns where it has to learn to score high on the evaluation set. And it can pick up robust features or non-robust features. So robust features would capture semantic understanding and reasoning and generalize to different distributions, while non-robust features that help with the task can capture, for example, the presence of particular words. And that helps when the inference data comes from the same distribution as the training data. So it picks up particular words. So for example, BERT models tend to learn to match the presence of particular words in a question. For example, when with the answer, for example, a date, without going through the steps of the reasoning process. One would go to find the answer. That is actually comprehending the text. And this is different for GPT-4, but we imagine it's not, it doesn't exist. And then something can classify that useless features, there's noise. And how can we evaluate whether the system is picking up robust or non-robust features? Whether it's making shortcuts. So we have this transformation that can be applied to a thing without changing it. So like we have a square, we rotate the square by 90 degrees, it's still a square. An object is some pattern that's invariant to transformations. And in a similar way, just as the rectangle preserves its angles and side lengths, it's possible to paraphrase a text. So here, the HPI was founded in October 1998. It's a public-private partnership. We transformed this into the establishment of HPI took place in October 1998 through a collaboration between public and private sectors. And this transformation preserves the label, which would be that it's an organization, and it's a particular organization. We can evaluate on both, if the system can handle both versions. The border between classes is not very well defined. So Oxford has a long history of excellence with numerous individuals benefiting from the resources and opportunities available. And some kind of decision boundary can be a bit iffy. Yeah, some example I made, another one about the HPI. So we have this original input text as HPI's private collaborator, HPF, takes on the role of the managing organization and stands as the only corporate member of HPI. Then it's an organization, it's the Hasselplattner Foundation. Maybe if we paraphrase it, we end up with something like this. Serving as HPI's private partner, HPF acts as the administrative authority responsible for HPI and remains its sole corporate member. I don't know, maybe this could be about a person. Who knows what person that could be? The computer doesn't know. Maybe I'll skip this to save time. But there, through. So just a little bit of math to explain how come the deep neural networks are so sensitive to perturbations. We can do all these magical things. We have a model, capital F, takes input X, and some epsilon, small perturbation. Then the Lipschitz bound is a constant, is a bound on how much the output of a model can change with respect to changes in its input. And this capital L is large for deep neural networks, which has to do with them being deep. They have a lot of layers, and each layer has a relatively high Lipschitz constant. And this results basically in, when we do a classification, we have the model F, and we add a classification function on top, on the end, after a softmax function. But anyway, the result is that there's no guarantee that the classification is the same when you perturb the input a tiny bit. So, yeah. Again, with a bird's eye view of my approach, I have a model pipeline, I have some data, and I made this perturber that applies these small epsilons to the evaluation data and the training data. And inspected how it affected the accuracy results. There are different approaches from which I chose the particular one I chose. There are actually quite strong rule-based baselines. I've programmed one, used one. But when I started working on this, transformers were the way to go. Looking at different transformers, one is called Luke. My colleague developed that one for it. I developed a Robusta model, fine-tuned for entity typing and entity context similarity. Then this interesting thing called Deep Type 2 came out. Just a non-transformer, uses relational knowledge, uses types. But yeah, all different approaches are doing the same thing in some sense. Oh yeah, and chose this because it's more data efficient. There are many ways to generate perturbations in language understanding. And it's easy for us to read. I think the border between data augmentation and adversarial learning is not very clear. Since adversarial attacks generate data points which are augmented data. The main difference is that the adversarial data are examples that the model tends to make wrong predictions on. So one way would be to add typos, like here. You can also swap words for other words. And use embeddings for that. I went on using thesaurus, like a dictionary that I made that's more reliable. And their generative methods are really good at it. I would have liked to paraphrase directly using GPT-3, but it wasn't there, it didn't understand Icelandic. GPT-4 actually understands Icelandic. So what I did was translate text from English to Icelandic, no, Icelandic to English and back to Icelandic, which perturbs the text, paraphrases it without destroying the meaning. For English, there are these evaluation benchmarks I mentioned earlier, general language understanding evaluation. Then there's the out of distribution version of it, and an adversarial version of it. Yeah, I kind of just made an adversarial version for entity tasks for Icelandic. But methodology works for English too. And a couple of papers that were training on perturbed data to improve models. Don't need to go into that. So what did I actually do? With a model pipe, I had a model pipeline, had a bunch of labeled data, and a paraphraser, a perturber. The model pipeline does entity typing, disambiguation, fine-tuned transfer learning. Data is kind of tricky to make. We used weak supervision, like semi-supervised stuff, and a multilingual baseline with a human in the loop to annotate effectively. But I guess we focus on the perturber, in which I used round-trip translation, translating, from German to English and back to German, a synonym dictionary to swap words. Steps. The first step was to create human-reviewed labeled data. Second step was to train models for entity typing and for entity disambiguation, and assemble them into a pipeline. Third was to build the perturber. This is a paraphrasing module, which could create perturbed data with different levels or degrees of perturbation, and apply that perturber to evaluation data and training data and evaluate the impact. So yeah, create an adversarial benchmark, test on, and create synthetic data to train on. Try to mitigate the drop in accuracy. See if that works. And also just create synthetic data, free data. So there are like 18 categories: person, organization, location, event, media, time, animal, instrument. I designed a method to map the Icelandic Wikipedia onto these 18 types. It was non-trivial, crawling links between pages, resulted in texts with the limited entity name and corresponding category. So Thora visited the famous Hallgrímskirkja church in Reykjavík. And yeah, this can be designated as a location, church, maybe organization. And I reviewed it to ensure correctness and exclusivity of the categories. We got like 105,000 labeled examples from this. This is the typing, entity typing. Then the disambiguation was a bit more complex. So I took all the paragraphs on the Icelandic Wikipedia, where each hyperlink from page to page serves as a labeled data point, because it's like a name in a given context that links to a page, which resulted in 105,000 samples. And then we labeled gold data, like human properly, yeah, it's called gold data, starting with a set of 48,000, a sentence of 48,000 names. The names were already labeled. We reviewed predictions from a multilingual model, entity disambiguation model, and confirmed what was good, resulting in 21,000 names, linked to Wikipedia IDs. And with the data, could fine-tune some models. So that, yeah, the trick, somebody had made pre-trained Roberta transformer model, 16 gigabytes of text, actually using a warm start, which first trained on multilingual data, and fine-tuned it to do sequence, like the transfer learning, to fine-tune it for sequence classification, to predict which entity type fits a name best, given some given context. And a similar way, I fine-tuned the same model to disambiguate, to predict which entity with a name best fits the context. The task is to encode candidates and input text and compute similarity between them, where the cross entropy between, like the cross entropy of the similarities was used as a signal. Having done all of this, I had this pipeline. Yeah, entity typing happens first, then comes the disambiguation, the end of the pipeline. Then to the perturbations. So large language models are good at entity tasks, They do it by embedding texts in a semantic vector space, but they are sensitive to perturbations, causing changes in predictions with small input text alterations. And the entity tasks should be robust against semantically preserving changes, such as paraphrases. So I created a benchmark to measure the entity model sensitivity to label preserving perturbations, namely the paraphrases. And that benchmark includes a training set, evaluation sets, and metrics to quantify text changes. So the perturber consists of 3 parts. So it translates text into English and back to Icelandic, preserving entity names and overall meaning. There's a synonym swapping module with grammatically correct substitutions, and then an error correction component using a model called Byte 5, fine-tuned on Icelandic error correction data and also synthetic error data. I combined the round-trip translation, synonym swaps, and the grammar spelling correction into a pipeline, which outputs different texts with the same meaning. You can generate synthetic data for any language tasks. You have to pre-process it in a smart way for it to work properly. Then translate to English, translate back to Icelandic, swap words for their synonyms, ensuring grammar is served. Then there's this error correction thing in the end. You end with a copy, not a copy, a perturbed version of the text. We wanted to measure the levels of the perturbation, which represent the change. Yeah. How big is the change from here to here? With higher levels indicating increased difficulty. So to vary the perturbation levels helps assess model robustness and sensitivity to changes in sentence structure and vocabulary. And the model was expected to struggle more with examples containing rarer words and more changed words. So I defined 3 metrics to measure the perturbation. The number of changed words, the change in average or median word frequency. So frequency meaning how common is the word in everyday language. And also the ratio of rare words. If I add a bunch of rare words to the thing, it should become harder. And slides were too complicated. The goal was to be able to move from less perturbed to more perturbed data. And the result were like evaluation sets that were less perturbed and more perturbed. And then also data that can be used for training. I scored each data point with these 3 metrics, X, Y, Z, the number of words changed, the word frequency drop, the change in the rare word ratio. I split it into tertiles with like 3 quantiles. It resulted in 3 times 3 times 3 possible values. This is like this cube that had different levels. And I segmented the cube into 3 parts. The less perturbed, the medium perturbed, and more perturbed. And so for example, 1.1.1 is less perturbed, and 1.2.2 would be medium, and 3.3.3 is more. I defined this through reviewing the output and making sure it fits my prior knowledge on what looks less and more perturbed, using like separate test data. But then I could use the less perturbed and more perturbed examples for evaluation, and the medium perturbed for training on. There's 3,500 examples in the less perturbed evaluation set, 3,000 in the more perturbed, and then there were 21,000 that could be used for training, which was to test basically it's useful to add these kind of paraphrased clones of the data. Can it help accuracy on the perturbed data? Can it help accuracy on the original clean data? Yeah, Jan LeCun said that data augmentation is a necessary temporary evil. From my experiments. Yeah. So how much does the performance of the models drop when evaluated on perturbed examples? And can we adapt the models to the perturbations and mitigate the drop in accuracy using data augmentation? Synthesizing data in a similar way if you know how it was perturbed, synthesize data and train on it. The goal was to investigate the sensitivity of the pipeline to perturbations. Step one was to assess the problem, to measure the performance drop, the perturbed and original data. We try to mitigate the problem. Training on perturbed data with the aim to increase robustness to perturbations, and then evaluate the effect of the mitigation. Assessing performance on the perturbed sets, and also checking the performance on the original sets, and ensuring that accuracy on the perturbed data doesn't come with too high a cost on the original unperturbed data. So these are kind of the main results. It's for this part, the other part. The paraphrasing intervention introduced a lot of additional errors compared to the clean data. It's kind of showing the point that like making it different, like transforming an example without breaking the meaning tends to break the model. There's a drop by like 10% in the less perturbed. So yeah, it's trained on clean data, meaning the original training data, and it drops by like 10%. And then for training it on clean and perturbed data, like transformed in the similar way through the same pipeline. And it didn't really help. And this is for the less perturbed. There's like, yeah, there was a drop. And then the more perturbed, there was a definite drop, higher drop. Yeah. And training on data perturbed in a similar way did not improve performance. So the paraphrasing intervention introduced a lot of additional errors compared to the clean data. The augmented data did not help mitigate the errors introduced by the paraphrasing. Yeah, then the data scarcity, and they're also about robustness. That how does accuracy vary by training set size on original and unperturbed evaluation data? Does incorporating synthetic data generated by paraphrasing improve performance? How does this improvement vary based on original training set size? I trained on different data sizes. I had 120,000 examples in total, and I selected subsets of it, 10,000, 50,000, and tried incorporating augmented data and not, checking the performance on both the original and the perturbed evaluation sets. And let's look at the graph. Okay, this is for entity typing, which is the first part of the pipeline. And this is just the average. That's probably the most readable one. So incorporating the paraphrase data, so basically at least the scales, I mean, it's only 3 data points. Scales with the amount of training data, and I kind of expected the, so in yellow is original plus paraphrased, so with data augmentation. So it's kind of what I expected, that incorporating the extra data or hope for would help. Had a significant effect on the 50,000 examples, not a significant effect on the smallest set. And it had an effect on the larger set. So it seems to have some impact. It needs to be controlled better or more. There's these 2 types of evaluation sets, the less perturbed and more perturbed. Split that into 2 parts. Like this relationship here, where it had a consistent effect to incorporate the paraphrase data for the examples that were more paraphrased according to the metrics. More original, more paraphrased. Less paraphrased original data, like the original examples unchanged, and then less paraphrased, actually paraphrased examples. Yeah, had somewhat of an effect, but not so much for the smallest data sets, which I thought would have the biggest effect. This is for entity typing. Then there's a disambiguation, which is the whole pipeline. And it had a, so there are graphs as well. So the paraphrasing intervention introduced a lot of additional errors compared to the clean data. The augmented data did not significantly help mitigate the errors introduced by paraphrasing. And training on more data didn't help much for this case. It felt weird for the disambiguation. There's a pipeline, similar pattern as in the previous picture. And it's actually a complex can be a complex relationship between the typing and the disambiguation. It's similar to before. Seemed to have an impact to train for the mid-size range. No significant impact here, and detrimental for the largest. And this is average for less and more perturbed evaluation sets. And we break it down. The original, the less perturbed, the original and less perturbed paraphrased. Paraphrasing had a bigger impact when it was more paraphrased. Well, we'll talk about this. Questions. Some inferences. Did the accuracy decrease for perturbed examples compared to the original ones? Yes, both for entity typing and for disambiguation. The less, dropped by around 10, 15%. Did it work to measure the different levels of the perturbation? Somewhat, as the drop in accuracy is higher for the more perturbed and the less perturbed. By training on data transformed similarly, can we mitigate some of the loss in accuracy for perturbed examples? And this was the case for entity typing, where the model always had a higher or equal accuracy compared to the original. With disambiguation, it didn't really work. How did accuracy change as the training size changed? For entity typing, there was a consistent increase in accuracy as the training size increased. For disambiguation, incorporating more data didn't have a big influence on accuracy. And I think this was just a problems with my disambiguation model. And did the paraphrased examples help? So incorporating paraphrased examples only increased accuracy on the original data significantly for 50,000 examples. Those in this picture, dot in the middle. No, anyway, it was not in a picture. It was in the table. I hope I answered the questions. So how much does the performance of trained models drop when evaluated on perturbed but semantically valid examples? So 10 to 20%, based on if it's less or more perturbed. Can you adapt the models to the perturbations and mitigate drop in accuracy using data augmentation? For entity typing, yes. For disambiguation, not so much, at least not using the model I trained, maybe for Luke, another model, which I want to repeat the experiments with. And number 3, how does accuracy vary by training set size on original and perturbed evaluation data? Tends to scale with the size, at least for entity typing. Does incorporating synthetic data generated by paraphrasing improve performance? It seems to do so for entity typing, especially when the training data is smaller. How does this improvement vary based on the original training set size? Impact was highest for 50,000 examples. We need to control for more factors than size. Yeah, a bunch of things like artifacts were developed to answer these questions. So entity typing, showed that entity typing and disambiguation similar. They're sensitive to perturbation similar to AdGlue, it's an adversarial glue benchmark. And if you train on similar data, drop in accuracy can sometimes be mitigated. And for the data scarcity problem, we used the multilingual model, weak supervision, and prior relational knowledge to create data. Used transfer learning to fine-tune large language models and develop this entity typing filter, which makes disambiguation accuracy relatively high with only tens of thousands of examples. The future, the GPT-4 has kind of changed everything because it understands meaning, not just superficially. And in my work using it, like it can handle, you can understand, it seems to understand the high level meaning regardless of some superficial small patterns. A problem with it is that it's just some black box in Silicon Valley we send queries to. And what I'd like to do is repeat these experiments now with Icelandic, which is this much better disambiguation model. And entity typing. That's something upcoming paper. Thanks.